Okay, in the previous video, we have seen our motivation to the boundary layer. This video, I'll just give you a quick summary on how to derive the boundary layer equations. Boundary layer equations, these are written in terms of non-dimensional parameters. U prime is equal to U by capital U, where capital U is the free stream velocity. V prime is V by capital V, which is the characteristic velocity in y direction. We'll come back to this later. X prime is X by L, where L is the distance along the x direction. But in case of an airfoil, you can say it as a quad length or something like that. Or if it's a flat plate, say the distance at which you are measuring the boundary layer thickness. And y prime is the boundary layer thickness at that particular x station. And we define this p prime as p by rho u square. Some people define it as p by half rho u square. Anything is okay. Just the equation will change slightly. Other than that, it doesn't create much big difference. Okay. Now, again, I'm saying we are dealing with the 2D incompressible flow only. So let's talk about first the continuity equation, conservation of mass, which is del dot u is 0. So dou a by dou x plus dou v by dou y is 0. If I um, if I just write in terms of the non-dimensional parameters, I'll get u by L times dou u prime by dou x prime plus v by delta into dou v prime by dou y prime is 0. We say that the gradient terms are of order 1, and hence we say that the order of this characteristic velocity in y direction is same as u delta by L. This is one important equation. Second is the u momentum equation. If you write again everything in terms of the non-dimensional parameters, we'll get some equation x. U prime dou u prime by dou x prime plus v by delta u by L v prime dou u prime by dou y prime equal to minus dou p prime by dou x prime plus mu by rho u L dou square u prime by dou x prime square plus mu by rho u L into L by delta whole square times dou square u prime by dou y prime square. Well and good. Now, you know that as we have seen this gradient term, this is of order 1. This is also of order 1. So, this whole thing is of order 1. This is also of the order 1, or you can say constant order to be more precise. And then we need to compare the orders of these two terms. What I would say is, okay, for large Reynolds number, that is rho ul by mu, mu by rho ul tends to 0. Hence, I'll say that, okay, this goes to 0. Now you may ask, okay, why doesn't this go to 0? Because I don't know what is the order of L by delta. So, now if I keep this also to 0, I'll finally get that this doesn't have any dependence in viscosity. Now we are developing some viscous theory, and finally we are saying that it is not dependent on viscosity, which is not true. So to get the non-trivial equation, what I will do is I'll say that the order of this should be equal to a constant order or order of 1, which is I'll write this as delta by L is of the order of 1 by root R. This is another important equation. In a similar process, if I try to write the V momentum equation, the algebra you can manipulate, I'm leaving that to you. If you try to write the V momentum equation, you will get two equations. Yeah, you will get one equation mainly, which is dou P prime by dou Y prime is 0, or P prime is constant across the boundary layer. Okay, as a summary of all this nonsense what I have discussed, which you may feel, the boundary layer equations are dou u prime by dou y prime plus dou v prime by dou y prime is 0, or v is of the order theta into u delta by L. And similarly, as I've told, this this term mu by rho L dou square u prime by dou x prime square, this will go to 0, and hence you will get this equation. The important thing to remember is delta by L is of the order of 1 by root Re, and then dou p prime by dou y prime is 0. Now this system is a system of non-linear differential equations because of these two terms. So finding analytical solution is difficult. In some cases, special cases, it is possible, but for most of the situations it is difficult. Thus, to get an approximate solution, we use momentum integral method, which I'm going to discuss in the next video. Thank you.